Hi there. In this video, I'm going to do a curve sketching example, and this is going to be a long one. But in this one, we're going to go through and figure out a way to sketch the curve of a graph, including all of the asymptotes, the intercepts, intervals of increase and decrease, local max-min, concavity, points of inflection, and finally put it all together and sketch a curve. So these are the steps that we consider A through G. We're going to sketch the curve as we go along rather than consolidate it all at the end. You're going to want lots of paper and probably hit pause a number of times as we go through. So the way your question would generally list this, if you're doing this university calculus or for my high school students, they give you the original function, y equals x over x minus 1 squared, and they want you to sketch the curve of that. Now, what I often do is, before I start, work out the first and second derivative, or sometimes you're lucky enough that it's given to you. Either way, you'll need those. If that is your challenge, you need to go look up a different video right now and not curve sketching, because I'm going to assume you know how to do left-hand and right-hand limits. We're going to assume you can do L'Hopital's rule and a limit as x goes to infinity, and also that you can do this chain and quotient rule and work all those derivatives out just fine. We assume those are the skills you already have. That would be assumed by the time you're doing curve sketching. Okay, so long story short, these are going to be presented to you. You see the first derivative, y prime, and the second derivative. And if they weren't given to you, you mutter under your breath and you go work them out yourself. Okay, so the things we need to consider the domain, the intercepts, and asymptote. So we'll start with domain. The domain of this function, you look for anything that makes a square root negative or anything that makes a fraction, the denominator of a fraction, equal to 0. So there's no square roots, there's no radicals to be dealt with. But I definitely see a denominator here, so we need to take that denominator, x minus 1, and notice that that cannot equal 0. So if we square root both sides, that means x minus 1 cannot equal 0. That means x is not allowed to be equal to 1. So my domain is all real numbers, except x cannot equal positive 1. Because if you put in positive 1, that function does not exist. So we'll move this out of the way. So there's my domain. We've got that set. Now we're going to calculate the intercepts. So doing the intercepts, we're going to look at, make x equal to 0 and solve for y. Doing that, you get y equals 0 over 0 minus 1 squared. You get 0. So if that's your x-intercept and y equals 0, then that's going to be your y-intercept as well. When you set y equal to 0, you get 0 equals x over x minus 1 squared. Cross multiply, that goes away. You get x equals 0. You get the same point like I told you you would. So 0, 0 is both your x-intercept and, of course, your y-intercept as well. Okay, so I've got a point right there. 0, 0 is my x-intercept, y-intercept. I'm going to go to my graph page, and I'm going to fill that in. So on my x-axis and y-axis, the point 0, 0, I got 1 point. Hey, one piece of information done already. Good times. So we go on to domain is complete. Intercepts are complete. Let's consider the asymptotes. Looking at asymptotes, part C, asymptotes. Well, to figure out the asymptotes, we can do the vertical asymptote first. It's the easiest one. The vertical asymptote, we've already figured out one of those points, because it's the point that makes the denominator equal to 0. What makes the function undefined, where the denominator is 0? We already determined that that happens at x equals 1. So that is a point on the graph where this blows up. That's the vertical asymptote. So at x equals 1, we have a point. I'll go to my graph. at x equals 1, we have a point where this function has a vertical asymptote. That was at 1 because I drew over it. Okay, so we have a vertical asymptote there. The next thing we're going to test is what does this function do as you approach 1 from the right-hand side, or the left-hand side, and from the right-hand side. So you do the left hand and the right hand limit to find out, is this function, we know it's either going to go up to positive infinity, or is it going to go down to negative infinity? And same thing on the other side. Is it going to go up here, or is it going to go down there? These are the big questions we got. We want that piece of information. So when you do that left-hand limit and right-hand limit, it's as inelegant as choose a value right here and find out what's the y. Choose an x value right there and find out what's the y. If you put in 0.9 and you get a really high x value or y value, then you're up here. And if you put in 0.9 and you get a negative, you're down there. It's a pretty simple concept. You're just trying to find out, are you going to positive infinity or negative? So we'll move these out of the way. We'll do a formal written, because this is a calculus teacher you're showing off for, so you want to make sure you write down all the steps. So we're going to write it in limit form. So we'll go back to our page, down here to the asymptote, and we'll write the proper stuff. So what we're trying to figure out now is the limit of our function as x approaches 1 from the negative side. And our function, if you recall, was x over x minus 1 squared. And we want to find out what is this approach. And then we want to do the same limit as x approaches 1 from the positive side. And the function is x over x minus 1 squared. So when we choose a number like 0.9 and evaluate it, you would get 0.9 over 0.9 minus 1 squared. And so you will get a number. You're really just looking for, is this going to be positive or negative? Okay, and this graph is clearly going to go up. You get a positive number, so that means it goes up to positive infinity. Okay. And then when you plug in a number on the other side of 1, so we plug in like a 1.1, just slightly bigger. On the numerator, you get 1.1. On the denominator, you get a positive, because it goes, you get a 0.1, which you're going to square, and that number also gets pretty big. You end up with a positive infinity. It's a positive number. So this limit is also positive infinity. Now, you might be used to seeing ones that if it goes up to positive infinity on one side, it goes to negative infinity on the other. But we're going to adhere to what we see. We'll plug it in and show. So as you approach from the left-hand side, this function is climbing up forever. And when you come on the other side, it was approaching positive infinity as well. So it seems to meet there somehow. Not sure what's happening, but that's what it looks like. So I'll leave the rest of the information. We just know it tends like that here, tends like that there. That's all the information I've got so far. So I need to move this stuff out of the way now. I want it to look pretty. Move in the 0.9. Give her a little erase. All right. So now I've got 2 points near my asymptote. We know it goes to positive infinity, and we've got that 0, 0 point. Okay, back to more work. Still on asymptotes. Once we've done a horizontal asymptote, well, we might as well figure out the vertical asymptote, or the horizontal next. We did vertical, so now we need a horizontal asymptote. To get the horizontal asymptote, you have to find out what is this function doing when x gets very, very, very large, or when x gets very, very, very small. So you want to do the limit of this function, x over x minus 1 squared, as x goes to positive infinity. When x gets freaking huge, what does this function do? So that is, if I rewrite this, limit as x goes to infinity, in the numerator you have x, and I'm just going to expand that bracket, x squared minus 2x plus 1. If you take x minus 1 squared, The only reason I do that is because you've learned in previous sections, you've learned L'Hopital's rule to do a limit as x approaches infinity. Your rule was to divide everything by the highest power of x. The highest power of x is x squared. So in the numerator, you divide x by x squared. In the denominator, you divide everything by x squared. So you get x squared over x squared minus 2x over x squared plus 1 over x squared. Now, why would your teacher tell you to do that? Because if you reduce this, you get 1 over x. This reduces to 1. The x's cancel here, and you get negative 2 over x and 1 over x squared. And the reason that was useful is because the limit of a fraction as x goes to infinity is exactly equal to 0. So now breaking this up, we know that that limit evaluates to 0. The limit of 1 as x goes to infinity is 1. And each of these things are fractions. So you get a plus 0 and you get a minus 0. So now I don't have to write the limit notation here because we are evaluating now, and you get an answer of 0. So that means as x goes to positive infinity or negative infinity, this function approaches 0. It doesn't equal 0, it gets infinitely close to 0. So at the line y equals 0 is a horizontal asymptote. So back to my graph, I know on here, on the x-axis, that is y equals 0, I'll draw it in red, you have a horizontal asymptote. And so you know that when x gets very, very, very large, this function is going to get really close to that dotted line. It's either going to get close here, or it's going to get close there. We're not sure which one. And out at this end, it's going to get really close here, or really close there. Now, you got to guess maybe. You might on this side look and see that it's tending up forever and coming here. So it's probably going to be up or down, but let's let the information tell us rather than guess. So I'll get rid of these because we don't know what it does. We're going to test what it does. Does it approach from above or below? Does it approach from above or below? We're going to go figure that out. Okay, back to my graph, way down here. So we have to now test. We want to test at x equals positive infinity, which is impossible, so we'll just choose a large positive number, and we'll test at x equals negative infinity, which means we'll choose a very small negative number, or a very large negative number, and plug those into the function. What's my function? It is still x over x minus 1 squared. So if you try positive 100 as an x value, that just gives you a number that's really large and lets you see how close you'll be. So you would get 100 over 100 minus 1 is 99 squared. This number is a positive, and so you're approaching, but it's almost 0. But it's a positive number, right? So you get positive like 0.01 or something. So because the whole point is whether it's positive or negative. Is it above the 0 or below the 0? So it is above the x-axis. So when x is very large, the y value is above the x-axis. When x is very large, somewhere out here, the y value is just above the axis. Okay, so we're out here at positive infinity. That's what my limit tells me. Back to the negative. We will choose negative 100 for x and see what happens to y. Negative 100 over negative 100 minus 1 squared is negative 100 over negative 101 squared, and you get a negative number now. Maybe it's 0.99 or something. Okay, but it's negative. So now you are below the x-axis, which means you're below the horizontal asymptote. Okay, so below when you are at negative 100. So we go out here. When we are at negative 100, we are approaching below the asymptote, not above. So we're not up here, we're down there. So there's that piece of information. Okay, so we've got our asymptotes tested. So let's move to the next step. Copy this and move it to a new page. We'll try that. Let's paste it. There we go. So we've now done all of the domain, all of the intercepts, and we're done the asymptotes. So now we need interval of increase and decrease. So how do we get interval of increase and decrease? We need to look at, for D, we need to look at the derivative. So let's take a look at what our derivative was. Okay, so we need that derivative. The y prime, if you recall, we got this at the beginning, was negative bracket x plus 1 over x minus 1 cubed. And what you're doing with intervals of increase and decrease, you're looking for where is the derivative positive and where is it negative. So we need to know where it's equal to 0. So we set this equal to 0 to find critical points. We take that up and multiply. You get negative bracket x plus 1 equals 0 because the denominator is gone. Divide by negative 1 both sides. 0 absorbs that, so you get x plus 1 equals 0. So you get x equals negative 1. All right, so before you go to build your interval table and you say, all right, so I just got one point to look at as a max or a min, and I know it's at negative 1. If you recall, the critical points were the points that made the derivative equal to 0 or undefined, which means x equals positive 1. You always test your vertical asymptote. So that vertical asymptote gets tested as well. So on a number line, I'm looking at testing the number 1 or negative 1. So my intervals are x bigger than 1. My intervals are between 1 and negative 1 or less than negative 1. These are the three intervals I need to consider and test this derivative with. Okay, so the way we set this up, we looked at x smaller than negative 1. We're testing x is between negative 1 and 1. And we're testing x is larger than 1. Now, what do I put across the top of my table is everything in my derivative. So often, most often forgot is this negative 1. I'm going to include it as a column. And then the x plus 1 as a column. And the x minus 1 cubed as its own column. And all together, we will analyze that first derivative and see what it's doing. Okay, so what's a good number to choose that's less than negative 1? Let's try negative 2. A number between negative 1 and 1, we'll choose 0. And a number larger than 1, let's choose 2 for symmetry's sake. All right, so the number negative 1 is always negative regardless of x. So that part's considered. Now, if we plug negative 2 into x plus 1, this value will always be negative. If we plug negative 2 into x minus 1, you get negative 3, and then you cube it, it is still a negative. So 3 negatives multiply together to give you a negative. That tells you that the function is decreasing there. Okay, now we choose our number 0. 0 into x plus 1 is a positive. 0 into x minus 1 squared is a negative. Or sorry, cubed. Squared it would have been positive, but cubed it's negative. 2 negatives make a positive. This function is increasing on that interval. So it increases from negative 1 to 1. Choosing a number 2, this is a positive. 2 minus 1 is 1. You cube, you get a positive. And altogether, I get a negative function. So over here, it is decreasing. So now I know where my function is increasing and where my function is decreasing. It's dropping in this interval, it's dropping on that interval, and it's increasing in between. So we can now determine, which is part E from this table, the local max and the local min. Because if it goes from decreasing to increasing, the function's dropping and then going back up again, that looks like a minimum. So we have a min right here at x equals -1. And we have a maximum where it goes from increasing to decreasing. We have a maximum at x equal 1. So we go to find those 2 points, and we're going to notice something pretty quick here. So we go to test those points. You think you have a minimum at x equals -1. So we need to find that point. You plug it into y equals x over, not y prime now, into y equals x over x minus 1 squared. You plug in the -1, you get -1 over -1 minus 1 squared, -1 over -2 squared, you get -1/4. So at the point -1 comma -1 over 4, you've got yourself a minimum point. So let's go we found a point, let's put it in the graph. It's exciting stuff. At -1 and -1/4, well, let's put it here. At -1, -1/4, you got yourself a point, and that point is going to be a minimum. So it's got to be the lowest point this graph hits. So -1 comma -1/4. You can label it right on there as the point if you feel like it. Okay, so there's a point. All right, so we're seeing some of the information. It's got to go through this red point and then through the black point and go up to infinity. I think we got some information here that looks consistent. That's looking good. So let's go back and look at our next min or max. We said we had a min there. Then you start to write that you have a max at x equals 1, and you realize how stunned that seems because x equals 1 was not in our domain. You said in the domain, if you recall, that x cannot equal 1. So you best not try and plug that in because it's not a point in the domain. So it can't be a maximum point. You have a min, there's no max. This statement does not make sense. X equals 1? Impossible. X equals 1 isn't an x value you're allowed to use. Alrighty, what's the next step then? The next step is F, concavity. Concavity and points of inflection deal with the second derivative. So for concavity, we're almost there now. Let me see if we can keep this under a half hour. The concavity means you look at the second derivative. The second derivative is 2x plus 2 over x minus 1 to the 4th. Set that equal to 0. Denominator comes up. You get 2 onto x plus 2 equals 0. Divide both sides by 2. You still have x plus 2 equals 0. Take the 2 over, and you get x equals -2. So at x equals -2, you've got this possible inflection point for you to test. Now, for concavity, you don't just test the point that makes the second derivative 0. You look at what also makes it undefined. As I mentioned before, you always test the vertical asymptote. And there was that vertical asymptote was at x equals 1. So when you're looking at intervals you test, you've got a point at +1 that you're checking, and this point at -2. So your intervals are bigger than 1, between 1 and -2, and less than -2. So a new table to set up, x less than -2, between -2 and 1, and larger than 1. So we look at what are the columns. The columns are what make up your second derivative. Your second derivative had a 2 in it. Feels kind of useless to include it, but you can. It had an x plus 2, and it had x minus 1 to the 4th power. And then lastly, I have a column to summarize what the second derivative was. All right, so what number would I choose smaller than -2? -3 is a great option. Between -2 and 1, choose 0. Bigger than 1, choose 3. Well, folks, 2 is always positive. And before I plug in anything, something to the 4th power is always positive. So I really need to consider the x plus 2. When you throw in -3, this is negative. When you throw in 0, it's positive. When you throw in 3, it's positive. So my second derivative is negative here, positive on that interval, and also positive in that interval. So here it's concave down. It's a frown. Here it's concave up. It's a smile. And here it's concave up, meaning a smile, like it opens upward. So it looks like where it changes from concave down to concave up, you have an inflection point right there at x equals -2. So we put therefore inflection point where it changes concavity, it occurs at x equals -2. We of course want to find out the y value. You plug that back into that original function, x over x minus 1 squared. So we plug in -2 and -2 minus 1 cubed, squared, sorry. So you get -2 over -3 squared is 9. So you get it at -2/9, which is about -0.2 repeating. Going back to my graph, one last point to put on. At -2, I have to go, this is -1/4, 2/9 would be, let's say, up here somewhere, a little bit closer. So now I've got all the information I need to fill in. So this asymptote, I'm going to move right up close to there, close to that axis, because my y values are pretty small here. So this function has to be from that inflection point, which I'll now make blue. From that point, it has to now open what we said it's going to be concave down. So it has to be curving downward. So it's doing a curve like that. After that, it is curving upward forever. So it's going to then curve upward, go through this minimum, go through that point, and climb to positive infinity. After that, we said this graph comes from positive infinity, and it's going to go out there to above the axis. There's no max min, and it has to be concave up, so it just meanders through here. We don't know those y values, it's just a sketch. And now we've included all of our points. We've got our graph. We have an inflection point here, which we probably should have labeled, -2 and -2/9. We've got our max min point here at -1 and -1/4, and we have that one lowly intercept at 0, 0. You've got your points. We've tested horizontal, vertical asymptotes. You've got your graph completely drawn. All of the steps covered. A through G, we've done everything. Congratulations, you've got yourself one curve, and it only took you a half hour to get it. Hope you learned a lot from this video and find a lot of other questions to practice. Good luck.